G'day. In this video I'm going to explain how to graph type 3 rational functions. Now, if you haven't seen my other videos, I'd better explain what they are. First of all, a rational function is a function in the form of a ratio or a fraction. And specifically, the function in the numerator and the denominator are both polynomials. So we don't have any trigonometric functions or anything weird, just polynomials. And when we talk about type 3, we're talking about a type where the degree of the numerator is greater than the degree of the denominator. So we have the more powerful function on the top. Now, type 1 was where the more powerful function was on the bottom. Type 2 is where they've got equal power, the same degree. And this one, the more powerful one's on the top. An example would be this. Here we have a quadratic on the top of degree 2. So the degree is the highest power. And here the degree is just 1. We normally don't write x to the power 1, but that's what it is. So our more powerful function is on the top. This is type 3, and I'm going to demonstrate graphing about half a dozen of these during the video. And you can watch whichever ones you like, or just settle back and watch the lot and learn some good graphing skills on the way. Now, if you've watched my earlier videos, you know that this form is good for finding intercepts, but if we really want to find the asymptotes, it's good to perform the division. And when we have a bigger power on the top, as will be the case for all of these, we're going to get a function of x. Not a constant, but a function. That is, we're going to have a value of x to the power 1, which would be a linear function, or x squared, which would be a quadratic, or even worse. And believe it or not, these become what are called oblique asymptotes. That's if it's a straight line. And if it's a parabola or a cubic or something, they become what are called curvilinear asymptotes. So, without any further ado, let's do this. I'm not going to go through the division process. I realise that took a lot of time in my previous videos. So I'm actually going to do it mentally. This one's actually quite easy because x times this gives us the first two terms. So it's x plus 1 over x minus 1. Subtract x from both sides. And this is the form that I like for finding asymptotes. If you want to go a step further, you could say that y minus x times x minus 1 equals 1. Just multiplying both sides by this. Now, you can see that neither of these two factors can be 0. Because if they were, you'd have 0 times something equals 1. And there's no number in existence that you can multiply 0 by to get 1. So neither of them can be 0. That means that if we graph this particular function, one asymptote is going to be where x equals 1, because that's what would create a 0 here, and that's something we just can't have. So we know that the line cannot exist there. And the other time is when y equals x. Now y equals x is a diagonal line through the origin, 45 degrees, y equals x. And this is what we call an oblique asymptote. This is a vertical one, of course. That's an oblique asymptote. I'll write this up here, O-B-L-I-Q-U-E. Now, where does it exist? Well, we have a positive x, a positive y, a positive 1, which means it's going to start in the top corner. So it's going to be here. And since these are normal asymptotes, we'll go diagonally across, just like on a chessboard or a checkerboard. And the second half of the graph will be here. And that's it. That's the end of graphing that one. Relatively easy, but something that's not taught really in New South Wales schools. I think sadly. But I get the feeling that it is taught in a lot of schools in the United States and elsewhere, so this is very much for you, or for anyone else that wants to learn graphing skills. There it is. Number one. Let's look at number two. Well, here's our second one. Now, I've already performed the division and rearranged the equation to get this. So these are equivalent statements. If I look at this one, it tells me two things about the graph. It tells me a few other things actually, but they're two very important things about asymptotes. By the way, when you do graph, and I encourage you to do a lot of hand graphing, I can see the merits of graphics calculators, and I can see the merit of computer programs in a particular sense, but I don't think there's anything quite to beat thinking a process out and graphing it by hand. When you draw your axes, please label them. Please put a scale on each and please indicate the origin. They are all components of a good graph. This tells us that x cannot be equal to -2. You can't have a 0 on the bottom. So -2 or -2, x equals that is an asymptote. There we go. Also, this cannot be 0. Notice we have a constant up here. So this can never be 0. That means y can never equal x minus 6. Because if you had x minus 6, take away the x and add the 6, it will become 0. Now x minus 6, I've realised I really need a longer, deeper graph here. I think I might change the vertical scale. I'm sorry to do this to you. I don't actually recommend it. So -6 will be here, and what's the gradient? 1. So it'll go through +6. Oh goodness. This is meant to be a 45-degree angle, but I've just distorted the vertical axis, so it's condensed. Otherwise our crossover point would have been way down off the board. Now again, positive, positive, positive. So we know we're going to get one part of the hyperbola here and another part here. We have an oblique asymptote here. Now because this is a 14, it's going to move further away from the centre of the hyperbola. So instead of coming right in here close, it's going to be up here somewhere. One would need to calculate points. In fact, what I didn't do is look at the intercepts. If x is 0, y is going to be -4/3, which is -1 1/3. -1, well there you go. Now we know where it crosses. It's a lot lower than I expected. So I'm assuming it'll go out here somewhere. Now if we substituted y equals 0, we'd have to solve this quadratic equation. and that's x minus 4 times x plus 1, so 4 and negative 1 would be the crossover points. Well, there's 4 and there's negative 1, so I've actually not quite drawn it properly. There we go. And that gives us a very good idea that this part will come to within about the same distance. So there's the other part of that particular hyperbola. I should stand on this side so you can see the graph. I'm sorry about the intercepts. I know I did that very quickly, but what I did simply was I factorised the top of this expression. So when y equals 0, I'm really solving this. And then it's just like with a polynomial, looking for the roots or the zeros. X would be 4 or negative 1. And there they are. They're the two values that make the y value 0. Well, that located that curve quite nicely for us. So let's look at number 3. Well, this one is rather more difficult. You can see we have a cubic divided by a quadratic, and when we've performed our division we get this expression. So we can see that one asymptote is going to be where y equals 3x minus 15, which is a straight line, and that's an oblique asymptote. We're going to have two asymptotes here at x equals minus 1 and minus 2, and this expression here is going to cause us some difficulty. They don't introduce this in schools very much, but this simply means that for certain values of x, the numerator here will be positive, and for certain other values it will be negative, and there's a certain changeover takes place. Now, putting all this together, drawing the asymptote at 3x minus 15, or y equals 3x minus 15, I realise is going to be a long way down the y-axis. So I'm going to go 5, 10, 15, 20. How's that? Five, 10, 15, 5, 10, 5, 10. So our first graph is y equals 3x minus 15. So it's 3 minus 15, and its gradient is 3, which means across 1 up 3, cross 1 up 3, or if you like, across 5 and up 15. So we'd go through here, through 5. Let's draw this in. That's better. I have a wedge-shaped pen and don't always get the blade right. So that's our oblique asymptote, and it's y equals 3x minus 15. Now, our two vertical asymptotes are at minus 1 and minus 2, so they're actually very close together. I'm regretting this already. I must say that I did these randomly. I just made up half a dozen equations, so I really should have thought this one out more carefully, but let's stick with it. Let's say that's one at minus 1, and minus 2 is very close by. My goodness. We'll see what this does. Now, if this was just a constant, if that's all it was, like 3 or 5 or something like that, if it was a positive constant, we would have our graph start here, move to this little panel underneath between these two asymptotes, and then move across to here. So it'll be like a checkerboard, because we have 3 across the top and 3 parts across the bottom. But this means that somewhere it's going to switch from being like that, as though it was a positive coefficient, to behaving as though it's got a negative on top. In fact, it will, like minus 3 or minus 21 or minus 284. Where does the changeover occur? Well, it occurs when this is 0. I've really done a bad job on this, haven't I? When is that 0? Well, it's when 10x plus 7 equals 0, So 10x is minus 7, so x is minus 7 on 10. So it's very nearly down as far as that negative 1 asymptote, minus 7/10. And where it cuts the asymptote, the oblique asymptote, is right there. Let's discuss what happens. To this side of it, the curve behaves exactly as we expect. We expect it to come in and go up the axis, but the problem is when it reaches minus 7 on 10, that coefficient becomes negative and it flips the graph upside down. So it comes down here and it may even start to bend. I'd actually have to calculate the values. It may even start to try and bend up the graph, but then it will plunge through that point at minus 7 on 10, at x equals minus 7 on 10, and continue not up the asymptote but down. So in other words, we've got this long part of the graph on the top side, on the positive side of the asymptote here, and then it passes through this point on the oblique asymptote and plummets down just to the right of the x equals minus 1 asymptote. Now there's no change of sign from here on, so we treat it just the same as we do all the checkerboard patterns. Because it's asymptotic down here, we go diagonally across and we have a portion of the graph in here. This is terrible for you, but just imagine it comes down that asymptote, does a bit of a loop and heads up the other one. So we've got this long, thin, I can't even draw that properly in there, long, thin part, and then diagonally across there we have another portion. Now, some of these graphs get too difficult even for Wolfram Alpha to graph, but I do recommend that you go to this site. I will certainly be going there after this video before I post it to check that my graphs are okay, although I must say that some of these graphs that I'm drawing, I'm confident Wolfram Alpha will not be able to draw, not in the detail that we have. But there it is. That's this particular one. Notice there were no squares anywhere, so the 3 simple asymptotes, 2 vertical and 1 oblique, but we had this interesting little feature here where we had a changeover. So this is fairly sophisticated already, but there's more. Let's have a look. Now remember that with type 3 rational functions, we no longer have horizontal asymptotes, but we have either oblique or curvilinear asymptotes. In this particular case, we have a curvilinear one. This is our first. The reason being that the difference in degree between the two polynomials is more than 1. If you divide x into x cubed, you get x squared. And sure enough, when you complete this division and rearrange, we get an x squared term over here with the y. So one of our asymptotes is going to be at y equals x squared. The other one will be at x equals 2. Now, that makes things look a little bit different. One, two, three, 4 might be enough. Hope they're far enough apart. Now, let's graph the asymptotes first. We have an asymptote at x equals 2. Well, that's easy. There's x equals 2. We just draw a long vertical. Well, that's meant to be vertical. This is hand drawn after all. The other one's going to be at y equals x squared. Now, I'm assuming if you're graphing rational functions that you know how to graph quadratics, and certainly y equals x squared. So it goes through the origin through 1, 1, through 2, 4, minus 1, 1, minus 2, plus 4. So we're going to have a parabola here which is an asymptote. That's a strange concept, but here somewhere along the track the curve is going to come up either underneath or on top of this one and get closer and closer as it goes out towards infinity. Which one it is we'll determine in a moment. But notice that it's divided the region into, divided the plane into 4 unusual regions. A very narrow thin little wedge here, rather unusual shape here, a large portion here, and a very peculiar one with a cusp or a point up in here. So we've got 4 regions that the graph potentially could be in. Now you notice they're not squared, so both these asymptotes are normal asymptotes. So our graph is either going to be here and here, or here and here, diagonally across the crossover point. We have a positive coefficient of x, a positive coefficient of y, and a positive number here, and it's a constant. So we're going to start on the upwards top right part of the graph, and part of it is going to be here. There we go. So far so good. Now diagonally down it means the other part is going to be in this region. Now this is going to be an asymptote, this is going to be an asymptote, so I know the graph's going to go down here and up here. But how is it going to manage this funny shape here? Well, the answer is the smaller the number is on the top, the closer it's going to go in, and if this was quite small, it will move way up into here and down. If it's a rather large number, you'll just get a very slight wave or a bend as it goes down. Now, one's fairly small, and I'm curious to know just where things go, which means I find the x and y intercepts. So I go back to my original form of the equation, and I'm going to substitute x equals 0 and y equals 0 to find the intercepts. Remember, the x-axis is y equals 0, and the y-axis is x equals 0. Let's substitute x equals 0 first. We've got x's in a few places, and if they become 0, we can cover them up, and we get y equals 1 over negative 2. That's minus a half. So we have an intercept at minus a half, or negative a half, on the y-axis. So we can see that our graph is going to be in very, very close, very tight to this parabola. Because it's only going to get closer and closer as we go up here, and it's only half a unit away at the origin. So my guess is it is going, in fact, to go up into here a little bit. So to find whether it crosses the x-axis again, we have to substitute y equals 0. Well, I'll replace y with a 0 here, and that means we have to factorise this. Now, normally factorising cubics is a real nightmare, but if you've learned about the factor theorem and the remainder theorem in polynomials, you might notice that 1 cubed, if we substitute x equals 1, 1 cubed minus 2 lots of 1 squared is 1 minus 2 plus 1, which makes 0. So x equals 1 works. There we go. And that confirms that this curve is going to go up in there somewhere. Well, if x equals 1 works, then x minus 1 is a factor. Now, to find the other factor, we need to perform another division. I'm going to do this fairly quickly. X into x cubed goes x squared, and that will give us a minus x squared. We need another minus x squared to get minus 2x squared. That gives us a plus x. There's no x here, so we need a minus x, and minus 1 times minus 1 is plus 1. I hope if I did that too fast for you, don't worry, you can do it on paper later. Now, can we factorise this? Well, not with whole numbers we can't. One way of testing, of course, we're getting back to quadratic theory, is to test our discriminant. Now, those of you who are a little more experienced with mathematics will recognise this quadratic equation because its roots are the golden mean of the two forms of the golden mean that the Greeks used. Let's have a look at the discriminant first of this quadratic. It's going to be b is worth -1, so it's -1 squared minus 4. A times c is going to be 1 times -1. -1 squared is 1, minus 4 times -1 is plus 4, so it's 5, which is greater than 0, which means we can take the square root. So if we're looking for the roots, sorry, not b, if we're looking for the roots, they'll be minus, oh, let's write the formula. There's our quadratic formula. And this part here we've already worked out, so we know it's going to be plus or minus root 5, because that b squared minus 4ac is worth 5. So we place that in. Minus b is going to be minus 1, minus -1. And 2 times a is going to be 2 times 1. So it's 1 plus or minus root 5 on 2. And if you put that through your calculator, that'll be 1.6180 and minus 0.6180. By the way, I chose this randomly. I just sat down and I do that with my examples. So it's quite fortuitous that it turned out this way. And there are our two roots. Let me encourage you to check on the golden mean or the golden ratio of the Greeks. It's a fascinating topic. Now 1.6 is going to be 1 up about here, and minus 0.6 is going to be about there. And these 4 points here confirm that our graph is going to be, goodness, it's going to be so incredibly close to the parabola all the way down here. I'm not sure I can even draw that well. We're doing okay, I suppose. And it's going to go up through this point and down through here. Now, actually I should have drawn that even closer to the asymptote. Now there's no guarantee that this point here at -1/2 is the minimum. It just passes through that point. It may actually be a bit lower to the right of it or something. But there's our graph of this particular function. It took a little bit of work to get there, but just rehearsing, by dividing we found the two asymptotes, and by seeing that the coefficients were all positive we knew which regions the graph was going to be drawn in. But then we had to go back and look at our original function to find the intercepts, the x and y intercept, to get a better picture of just how to draw this. And that took us some time. But I hope that's made sense and helped. And this was our first experience of a curvilinear asymptote. And as you can see, it makes a little bit of an interesting difference to what we've got. Now I do have some more examples to show you. I think the next one, I can't see where I've written it, but the next one I wrote out, I think from memory, has a double asymptote somewhere. So let's have a look at that one. Well, it's not what I remembered. The one with double asymptotes comes next. This one has another problem. When we look at the original form of the function, you can see that the degree of this polynomial is 3, the degree of this one is 2. The difference is 1, so we're going to have an asymptote of the form y equals x to the power 1. That is a linear function. y equals something, mx plus b or something. And sure enough, when we perform our division, we get this. Y equals x will be our asymptote. But you notice that something unusual has happened here. The denominator has changed from x squared minus 9 to x plus 3. And I want you to notice this. That when we factorise the top and the bottom, the top factorises as x minus 3, because this is a difference between cubes, times x squared plus 3x plus 9. And the bottom factorises, because it's a difference between squares, as x minus 3 times x plus 3. Now, if you're observant, you notice that two factors are the same. One in the numerator, one in the denominator. Which means that we could just go ahead and divide them out, except they're not constants, they're functions. And we have a problem when x has a certain value. Can you see what it is? Well, I hope you can see that when x equals 3, we're going to have 3 minus 3, which is 0 on the top, and 3 minus 3, which is 0 on the bottom. And 0 over 0 makes no sense whatsoever. So we make the little observation that x cannot equal 3. Just can't. Makes no sense whatsoever. Once we understand that and agree to that, for any other value of x, we can divide this out, because they'll be identical numbers. And then we just go ahead and perform the division and get this. So we have to notice that x cannot be 3 in this original function. And that changes our graph very, very slightly. Let's have a look. I'll put some units on first. 4, 1, 2, 3, 4, negative 4, 1, 2, 3, 4. So we have one asymptote at x equals negative 3. Let's try and draw that in. And we have another one where y equals x. Now y equals x is going to go through negative 3, and 0, 0, and 4, 4. They're all going to be the same. So here we go. There are our two asymptotes. Now, because we have a positive coefficient of x and a positive coefficient of y and a positive constant, we know the graph is going to be in this upper right hand section and the bottom left hand section. So we're going to have an hyperbola. The 9 means it's moved some distance away from the centre here. Now it may or may not touch the axis. In order to solve that problem, we would need to set y equal to 0 and look for the intercepts. We'll have a look at that in just a moment. Actually, let's do that right away. Once these are gone, what we're really looking for when we set y equal to 0 is for this to be 0 or that to be 0. Remember, we're not allowed to have the x minus 3 equal to 0. Now, for this to be 0, we need to check whether it can be factorised. So let's look at our discriminant again, because it is a quadratic. B is worth 3. And a times c is going to be 1 times 9, which is 9. That's going to be 9 minus, that's a terrible 9 there, 4 9s are 36. Well, that's negative 27. That's definitely negative. And that means we cannot take the square root of it in the real number system, so there are no roots. What that means is the graph doesn't touch the x-axis. Now, how close it gets, I don't know. We could look at the y-intercept. Let's do that. If we substitute x equals 0, we get minus 27 over minus 9, which is plus 3. So it definitely goes through +3 here. So my guess is the graph does... Ooh. The board moves as I press on it. So there we go. It probably does something like that. And I've got a problem now in that the bottom portion of the graph should be about the same distance away, but that's going to be off the board for you. So I'm just going to fudge a little bit and just draw the bottom part just within sight. But that is our graph, except for one thing. Remember this. What we've graphed is this function, that rational function. But just by putting this in, does something rather intriguing. It means that where x is worth 3, we can't have any value. So if we look right up to the graph up there, we have to rub out a value and put a hole in the graph, a gap. Now it's infinitesimally small. We draw a big circle, but we can get up to within billionths and quadrillionths and vigentillionths of it and so on. But it nonetheless has no value at x equals 3. That is now a picture of this original graph. And just to make the point, if I wanted to poke a hole in it here, above -1, all I would have to do to my original equation is multiply it by x plus 1 over x plus 1. Now for any other value of x, they will divide out because they're equal to 1. Same number over the same number. Will make absolutely no difference to the graph or the function, except now if x is -1 or -1, we would get 0 over 0, which would cause problems. So at -1 or -1, we no longer have a value. And we could keep poking holes in our graph. If I wanted one here at -4, I would just multiply by x plus 4 over x plus 4. And I could just keep working along and plugging holes or poking holes in my graph and as much as I wanted. But that's a very simple technique. So when you see this happen, when you get an expression like this and factorise it and see this, you should recognise that you can divide those out, but it's going to mean there's a value that is not legitimate, and it's going to leave a gap in your graph. So that's been worth seeing, and I hope that's a good lesson. Now the next one does have a double asymptote. In fact, I've got 2 more examples. I know these are long videos, but there's nothing like watching someone graph and discuss the graphs to learn good graphing techniques, apart from practicing them yourself. The next 2 graphs I designed just for a bit of fun, and I have actually drawn them myself as a practice, and I've gone to Wolfram Alpha, and Wolfram Alpha is incapable of graphing them. So you're going to have to trust me that they're right. You can substitute some values of x to test me, but let's have a look at them. Well, one good dose of hay fever later. I think I'm allergic to my new cleaning fluid. This particular equation is rather dramatic, and I've chosen it and the next one to round off our series because they're difficult, yet fairly simple in a way, when you understand the principles you're looking for. Now, I've already performed the division and got the asymptote, the oblique asymptote here. Remember, our type 3 rational functions don't have a constant, they have a linear or a quadratic or a cubic function or something of that nature. In this case it's a straight line, so we're going to have an oblique asymptote. I don't have my original form, it's very complex, but we're going to analyse this and learn what the graph looks like. By the way, I did mention, I think, this one and the next one, if you type them into Wolfram Alpha, you'll find that the program cannot cope with it. It can't actually graph this function. So you'll have to trust me a bit and substitute some values. Let's have some fun. Now, x is going to go from plus 6 to negative 4 or minus 4. So let's 2, 3, 4, 5, 6. And I'll just do the y-axis on the same scale. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Pardon me. Let's draw our vertical asymptotes. We have one at x equals 3, which I'm going to draw quite a long one because I'm expecting to have some issues. There it is, right the way down. Notice, I hope it didn't escape your attention, that it's a double asymptote. We have a square here. And as I did in my other videos, I'm going to highlight double asymptotes with red. Still an asymptote, but it's just to remind us that something special happens here. And that is, instead of having curves opposing each other like this, we're going to have them both wanting to go down or both wanting to go up the asymptote on either side, a bit like a mirror image. So we have one there. We have another asymptote at x equals 6. There we go. Whoops. Another one at negative 1 or minus 1. That's here. And you notice it's doubled, so I'm going to get my red pen again and highlight it. So it's a double asymptote. And the last one is at x equals negative 4. I hope you're starting, if you've been watching this series, that you're starting to anticipate what's happening and see how the graph unfolds. There are our vertical asymptotes, 1, 2, 3, 4. 2 of them are doubled. So we've already highlighted them. Let's look at our oblique one. Our oblique asymptote is y equals negative 2x plus 3. So it's got a y-intercept of plus 3 and its gradient is negative 2, which means we go across 1, down 2, cross 1, down 2, cross 1, down 2, and let's keep going, cross 1, down 2, cross 1, down 2, so it'll be minus 7, cross 1 and down 2, which will make it minus 9. Cross 1 up 2, so it'll make it level with 5, and if it's going to go across 3, it'll go up another 6, so from 5, 6, 7, 8, 9, 10, 11, it'll go through there. Now, I'll do my best. Not the straightest of lines, I realise, but there it is. That's our oblique asymptote. So we've got 4 vertical, 1 oblique, and we have on the top 2 potential change of sign terms. You can see we're going to have a change of sign when x is worth 2, because 2 minus 2 is 0. So when x is worth 2, I'll switch to purple. When x is worth 2, on the oblique asymptote, or sometimes it would be horizontal, but with type 3 functions it'll be oblique, the curve is going to want to touch the asymptote there. Now it can't touch it at either end, but it can cross or touch in the middle. Notice that when y equals minus 2x plus 3, that becomes 0 on the asymptote. And when x equals 2, that becomes 0. So we have 0 equals 0. It doesn't matter what the rest of it is, that's 0. Now another value that would make this 0 would be x equals negative 2. Here's negative 2. So we go up and we're going to have some issues there. Notice, however, that this term is squared, which means that when you go from one side of negative 2 to the other side of negative 2 and square the result, this is always going to be positive. You're not going to get a change of sign. So the graph is actually going to touch the asymptote here, but it's going to want to remain on the same side. We'll see what that means. Now let's find out where the graph starts. I've factorised it in such a way that all these coefficients are positive except for this. So it's like we start with a negative coefficient on the top, which means we don't start on the top right, we start here in this section. So we're going to have our first portion of the graph on the right hand bottom side because of that negative. Now we have two normal asymptotes, so my next part of my graph is going to be in this little panel. I'm going to draw it as best I can. It's going to be very long and thin, and the whiteboard moves a bit, quite apart from the fact that my gross motor skills could do with some improving. There we go. Now, we would expect it to cross over, but remember this red line, we have a double asymptote. Because it's a double asymptote, we expect it to work towards the asymptote as a mirror image of the one on the other side. Now that means, normally, there's our next asymptote, and we have this. We would expect this part of the graph to be here, but we have this changeover point, and it's a normal one, which means we get a genuine changeover of sign. So this will come down and bend and want to go back up here, but it will reach this point, touch the asymptote, and go up on the other side, and instead of going up, the asymptote will go down. It's as though it's been flipped entirely upside down. So that dot, this, causes a flip, a reversal. And instead of going up here, it's now going down here. We have a double asymptote. So this is going to behave like this, like a mirror image. And again, we would expect this to go up and do this, but we have this point. So it's going to travel up the asymptote. It's going to reach the asymptote at that point. But unlike the first one, because this is doubled, or squared at least, it's what we would call a double changeover point, it will never ever change sign. It'll always be positive or 0. So once it reaches its 0 there, it will come back on the same side and head back down the asymptote here. So instead of being fully contained, it will actually touch the asymptote at that point. Now these are normal asymptotes, so the last bit will be here. Now, to find exact values, you would have to substitute x values. Actually, if we wanted to know this exact value here, we would have to substitute x equals 0, the equation for the y-axis. And unfortunately, I don't have my original form of the equation here, but if we put x equals 0 in this, we would get y, just remove that because 2 times 0 is 0, y minus 3 will be minus, and let's put a 0 in all these terms. 0 in here leaves a negative 2, 0 in there leaves a 2 squared, 0 in here, negative 3 squared, negative 6, plus 1 squared, and 4. Don't need the plus. Gee, that's grubby. Now, what have we got? Well, 2 squared is 4, and we've got a 4 on the bottom, so let's get rid of that very quickly. We get minus 2 is plus 2. Minus 3 squared is plus 9. 1 squared is 1, so that's not going to make any difference. So we have 9 times minus 6 is minus 6 nines are 54. Add 3 to both sides, and we get y equals 3 minus, now 2 on 54 is 1 on 27, so that's going to be 2 and 26/27. So it's just below 3. Well, there's 3, and you can see, goodness me, just below would mean this would actually have gone way up in here and down. Very, very sharp. And probably all these other ones are going to do the same. So substituting can help you get a more accurate picture, but the graph nonetheless is in all these places with this basic shape. And I think that's quite dramatic. It's unlike anything you normally graph at school, but you're learning some very good graphing principles of rational functions. And if you can handle these, then when you see the kinds that you get given in school tests, mostly you'll find them very straightforward indeed. One to go, a bit more of a challenge, and again it's one that Wolfram Alpha can't graph. Let's have a look at it. Okay, here's the last one. As you can see, it's a very similar structure again. The division has taken place, and we can see that again it's type 3, which means that we don't have a constant, which means we don't have a horizontal asymptote. This time our asymptote is a parabola, so we have a curvilinear asymptote. But we've got 3 vertical asymptotes, so we'll look at those. I'll try and draw them fairly quickly. Now, the numbers aren't huge, fortunately, so let's go 1, 2, 3, 4, 5, 6. Okay, we have one asymptote plus 6. I think I've just determined what's going to be a bit of a problem here. This parabola is going to go skyrocketing and not reach here, so I'm going to have to do a little bit of a fudge. X equals negative 5 will be another one. Negative 5 is over here. And it's a double, so let's get our red pen out. I'll put this on so we've got a reminder. Otherwise it's very easy to forget. And negative 1 is our other asymptote. So there are our three vertical asymptotes. That's 6, negative 1 and negative 5. And negative 5, of course, is double. So we've got our vertical asymptotes taken care of. Now this asymptote is where y equals x squared minus 4. So this is an x squared parabola shifted down 4 units. So instead of going through the origin, it goes through 1, 2, 3, negative 4. And it'll still have the same shape. Cross 1 up 1, cross 1 up 3, cross 1 up 5, and so forth. Cross 1 up 1, cross 1 up 3, cross 1 up 5. Now, if I drew this properly, it would reach this asymptote way above the board. So I'm going to have to change the scale a bit. Perhaps if I call this negative 2 and negative 4, negative 6, negative 8, then it's going to go through negative 4. This point, now we do 2, 4, 6, 8, 10, 12. So now it's going to go through roughly 5. That's better. Goes through 1, 2, 3, 5. So what it's done is it's lowered the points down. I'm going to get a shallower parabola. Actually, even with this, I'm still going to have to fudge it a little bit. There we go. And so it's not really as curved as it should be. I just realised my scale's not going to help. But this will at least give us the picture. I'm just going to remove that for a moment. That's just helped us get our asymptote. So we've got our three vertical asymptotes. We've now got our curvilinear asymptote. What's this telling us on the top? Well, it's telling us we've got a change of sign. We've got one happening at x equals 3 and one happening at x equals 5. Now you can appreciate, you can change these as much as you like. There's x equals 3, so it's somewhere right there on that asymptote, and at 5 on the asymptote we're going to have a normal change of sign. And since we have plus, 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 and a plus out the front, our graph is going to start in this top right hand section up here, and I'll graph it in purple. So we're going to have the first part of our graph will be here. So far so good. So it's asymptotic up this vertical asymptote, and it's asymptotic to the parabola on this curvilinear asymptote. They're both normal asymptotes, so we would have the next part of our curve over here, and it would be diving down there like, whoa. It's a problem when you can't draw straight lines. And we would expect normally for it to come down and down here. But we've got a problem. When it reaches x equals 5, the sign changes and it wants to behave. Let's do it a little bit in green. It wants to behave as though it was up here. That's what it wants to behave like. So it's going to jump through the asymptote here and try and follow this line down to head back up. But once it reaches this point at x equals 3, there's another change of sign, so it ducks back through. And it ends up not continuing there, but actually heading back down again. Now, not only that, it's got to follow the parabola around a little bit and do that. So this is a most unusual shape. How about that? So it's up, jumps across the asymptote, travels along for a bit, jumps back down, follows around underneath, and it's got to follow that parabola around. Pardon me. Now, normal asymptote. We don't have any more change of signs over here, so the next part's going to be here and quite normal. There we, whoops. And because this is a double asymptote, what's it going to do? Instead of going diagonally across, it's going to act like a mirror image, and we're going to expect to have the two parts of the graph go up there asymptotically, which means the last little portion will be in here. Actually, probably come way down into there. Oh, that's really messing it up, isn't it? But anyway, what an amazing looking graph that is. That is this particular graph. Now, that's the end of my series on rational functions. I think I've covered them much more thoroughly than most school students would require, but I've tried to emphasise what the vertical asymptotes are telling us, what double asymptotes tell us, the kinds of horizontal, oblique or curvilinear asymptotes we can get over here, and what these tell us up here. Most school questions will have a constant there, which means you're not going to cross the asymptotes at all. But if you do see a factor like this, just hopefully you know how to handle it. I am going to produce a couple of other videos because I'm just on a run here exploring this, and I'm going to show you, for example, a graph that does this all the way up. Well, not all the way, but for a certain part of the graph. That's coming, but not in this particular video. We've gone long enough. I hope it's been of value. If you've found it useful, please like the video. Please leave your comments. As I say, I always enjoy reading them, as long as they're constructive, good or bad. And if you have not already subscribed, then please subscribe to my channel so you can hear about future videos. As always, I thank you for watching.